Have you heard the joke about engineers saying that sine of x equals x? It's on a shirt, so it must be true. Of course, that's absolutely false. What they're really saying is that sine of x is approximately x for small values of x. Looking at a graph of sine x and the line y equals x, this approximation is telling us that the line approximates the values of sine well, as long as we're close to 0. So we can use this approximation to speculate what the limit of sine x over x is as x approaches 0. Since x is close to 0, sine of x can be approximated by x. Simplifying, we find that the limit is 1. So this is a good engineering student's guess for the limit. It turns out to be correct. We'll be using the Squeeze Theorem as covered in the previous video to prove that this limit is 1. Using a unit circle, geometry, and trigonometry, we're going to find two functions, g and h, functions of theta, so that sine of theta over theta is between those two functions. Let's focus on the blue segment in the figure. That segment is perpendicular to the horizontal axis, so that together with the radius and the horizontal axis, we get a right triangle. We are interested in the opposite side of this right triangle, and the hypotenuse is 1 because we're dealing with a unit circle. We want to relate the opposite side of this triangle to theta, so we're going to use sine. And we see that the opposite side, the blue segment we're interested in, is sine of theta. Next, we're going to look at the circular arc that's in orange in the figure. We want to express the length of the circular arc in terms of theta, and we're going to use a well-known geometric fact. The arc length is equal to the radius times theta in radians. We have a unit circle, so that the length of our circular arc is just theta. Now we look at the green segment, a segment which is part of a tangent line to the circle from the point of tangency to the intersection with the horizontal axis. This segment is part of a right triangle, where the side we're interested in is opposite the angle theta. We know it's a right triangle because every line tangent to a circle is perpendicular to its radius. Using tangent of theta in this triangle, we get the tangent theta is opposite divided by the adjacent side, which is our radius 1. So the opposite side is simply tangent of theta. Using the figure or geometry, we see that the blue segment is shorter than the orange segment, which in turn is shorter than the green segment. So we get the inequalities that sine of theta is less than or equal to theta, and theta is less than or equal to tangent of theta. We are going to manipulate these inequalities until we get the desired functions g and h. Let's start with sine of theta is less than or equal to theta. We'll divide both sides by theta, remembering that theta is not 0 because we're taking the limit as theta is approaching 0, and theta is positive because our theta was in the first quadrant. This is relevant in that we can't divide by 0, so theta shouldn't be 0, and we want to divide by a positive theta so as not to change the direction of the inequality. Next, look at the inequality theta less than or equal to tangent theta. We write tangent as sine over cosine. Now multiply both sides by cosine and divide both sides by theta. Again, keep in mind that cosine of theta is positive and theta is positive when we're in the first quadrant. So on the one hand, sine of theta over theta is less than or equal to 1. On the other hand, sine of theta over theta is greater than or equal to cosine theta. And there we go. So we found g of theta is cosine theta and h of theta is equal to 1. But we really should convince ourselves that this inequality holds even if theta is negative. Consider a negative theta in the fourth quadrant. Theta then can be expressed as the negative of the absolute value of theta. Consider the expression sine of theta over theta. Use the fact that sine is an odd function. The -1 factors cancel out. We've derived these inequalities for positive arguments in the first quadrant. Take advantage of the fact that cosine is an even function and that theta is defined to be the negative of absolute value of theta. Substitute in the above inequality, and we get the desired result even if theta is in the fourth quadrant. Of course, we can just take a look at a picture of this. In the next step in the squeeze theorem, we'll be taking the limit as theta goes to 0. On the right, the limit of a constant is the constant, so we get 1. On the left, we evaluate the limit directly, and as theta goes to 0, cosine of theta goes to 1. So our limit is a quantity between 1 and 1, so the limit is equal to 1 by the squeeze theorem. In the next video tutorial, we'll be working through examples using this special trig limit. For example, what is the limit of sine of 5x over x as x goes to 0? Is it still equal to 1, or is it something else? Can you guess the answer? By using the approximation that sine of 5x should be approximately 5 times x if x is small. See you next video.